Let's solve this equation right here using the graph that they give us. So basically what they tell us is that this rational equation has two parts. The blue graph is the rational equation right here, so you're thinking of it as y equals 2 over x plus 1. If we were, let's call it y1 like they do. If we were to graph this equation or function, it would look like having these two branches with, as you can see, a vertical asymptote of at x equals 0. So that's where it's undefined. That's why it doesn't touch, it doesn't go through that vertical line x equals 0. Now the next one that they show us is y2 equals 3. So I basically have the graph of the left side, the graph of the right side, and using the graph, the solution really involves no work whatsoever other than realizing that when is y1 equal to y2 means when do the graphs intersect. And it looks like that happens right here. So where do they intersect? They intersect at 1, 3, and since this equation is in terms of x, we're basically looking for what is x. So x in this case is 1. So by using the graph, all we do is we pull out the intersection point and keep its x value. What if we had to solve this symbolically? I would take my equation 2 over x plus 1 equals 3 and say, well, the LCM looks to be an x, so I'm going to go and multiply each term by x. And when I do that, some cancellation occurs, only in the first spot where I need it. That's going to give me 2 plus 1 times x, 3 times x is 3x. And notice if I continue and solve this for x, I get the same that I got from the graph. So visually, without any work, we can pull out what the solution of this equation is if the graphs are provided. Let's look at some rational equations and their applications. For instance, one of them is solving formulas for the indicated variables that they require. The first example says solve this equation for t. So basically all I care about is t acts like my variable. Everybody else here is really just like a number to me. So since it looks like I have a fraction equal to another fraction, instead of using the LCM, I'm going to make use of the cross product. That's going to give me 1 times t plus 1 equals 1 times r. So that's just t plus 1 equals r. And remember, since t is my variable, if I just subtract 1 from both sides, I get t equals r minus 1, and t is isolated, completely solved for in terms of r. Part B requires a little bit more work. We're supposed to solve this for r2, so r2 is the one that acts like a variable. All these other ones are essentially numbers for me. So what I'm going to do is use the LCM, and the LCM is all factors r, r1, and r2. They're all different variables, so they act all together as factors of my LCM. So I multiply each chunk by the LCM in hopes of some cancellations to occur, and it looks like I can get rid of r in the first one. In the second term, the r1 goes away, and in the last term, the r2 goes away, giving me r1, r2 equals r2 plus r1. So now all the denominators are gone, and remember my goal is to solve for r2. So I have my eye on r2, which is occurring here and here. So it's not as easy as dividing by r1 and being done with it, because I have an r2 on that side also. Now I'm going to go get all of them on the same side first before I do anything. So r1, r2 minus this other guy r2 equals r1. Now I'm almost there. I just have to pull out r2 by itself so that I can isolate it. And if you notice, the left side, these are not like terms. They have different variables. They do share in common, however, r2. So I'm going to factor that out. When I pull that out, I have r1 minus r left over. So what I did was I yanked down r2 so it could be by itself multiplied by some chunk equals r1. And now again my eye is on the r2. I want to have the r2 solved for because that's what I'm supposed to solve for. And I can go ahead and divide by this ugly stuff to get the r2 all by itself. So r2 is equal to r1 all over r1 minus r, and r2 is completely isolated in terms of the other variables, so I am done. Remember, don't cancel the r and the r and the r1 and the r1, because although I have a product in the middle, the bottom, these two pieces are linked together and I can't split them and cancel them. Let's go look at an application. It says, suppose a person mows a lawn with a large push mower, I guess in 5 hours, whereas the same lawn can be mowed with a riding mower in 2 hours. Write an equation whose solution gives the time needed to mow the lawn if both mowers are used. So we're using two machines, and each one has its own rate. So there's a fast one and a slow one, and together they get a job done. So how do we go about this? Let's just focus on the first one, on the large one. If we think about it in terms of, think of it hourly, let's say. In 1 hour, one-fifth of the job is done, if we think about it, because it takes 5 hours for the whole job. In 2 hours, 2/5 of the job is done just by that one large one. In 3 hours, 3/5 of the job is done just by the large one. In 4 hours, 4/5 of the job is done. And in 5 hours, of course, 5/5 of the job is done, which is the whole job done. That's just looking at the large one. Only the large one is what we're focusing on. Now what if I say in T hours? That would be, how much of the job is done? T over 5 of the job is done in T hours, just with the large one alone. Now for the small one, we do the same idea. If I use the same idea, in 1 hour, I have half the job done because the total job was done in 2 hours, so it makes sense that in 1 hour half the job is done. And in 2 hours, whole job is done. But now I'm thinking, what happens in T hours? Since these guys are working together, T over 2 of the job is going to be done for the second one. So here's what's going on. The question says both mowers are used. So if both mowers are used, it's going to take them T hours. Let T be the hours for both to get job done. So basically in T hours, T over 5 of the job is done with the large one, and with the other one, T over 2 of it is done. So I guess this one is the faster one because it only does it in 2 hours. This one is the slower one. Now T is the total time for both of them together, which means both of them together need to get the job done. So I'll say first one plus second one gets whole job done. So here's the part by the first one, T over 5, plus here's the part by the second one, T over 2. And remember, the whole job done always meant the entire job is done. So anytime you're getting the whole job 1, you're going to equal it to 1. So part of the job by the first one, part of the job by the second one equals the whole job done, and t is the hours that it takes for them together, which is what we were supposed to do. That's part A. Part B says solve it. Well, solving it is not going to be that bad. I'm going to multiply everything by the LCD of 10, it looks like. And some cancellation occurs. 2, 5. So we end up with 2t plus 5t equals 10. That's 7t equals 10. Divide by 7. And t is equal to 10 sevenths, or 1 3/7, or t is equal to 1.43 hours for both of them to get the job done, which makes sense. One of them was in 5 hours, the other one was in 2 hours, so together they should take less time than even the one that was doing it in only 2 hours. Okay, let's look at another application. It says, in still water, a tugboat can travel 15 miles per hour. It travels 36 miles upstream and then 36 miles downstream in a total time of 5 hours. So we're going to organize our thoughts in our distance equals rate times time chart. Distance equals rate times time. I'll say it goes up and then it comes down. Going up is 36 miles for the distance, and then coming back downstream is also 36 miles. Find the speed of the current. So I'll say x is equal to the speed of the current, because that's what I'm supposed to find. Total time, this is keyword, total time is 5 hours. I'll mention that like that. And then it says the speed of the tugboat is 15 miles per hour. So when it goes up, it goes slower because the current is trying to stop it, and when it comes down, it goes faster because the current is helping it. Well, by itself it was going 15. But if it's being faster pushed by the current, there's another additional x miles per hour. And when it's coming back up and being slowed down by x miles per hour, I subtract it from the rate. So going down, add the speeds, going back up, subtract the current from the boat. Now I have distance and the rate. I can solve for time. Time is distance over rate. So here's my distance, here's my rate, here's my distance again, and here's my rate. And last thing I use is total hours. So what do I do with the time? 36 over 15 minus x plus 36 over 15 plus x equals the total time of 5 hours. And then I solve this using the LCM of 15 minus x, 15 plus x. So we're going to multiply all terms by the LCM. These guys cancel away, these guys cancel away, nothing cancels there, and we get. Then we distribute and do any cleaning up that's involved. I'm going to multiply these first. That's going to give me the left hand side where it looks like the 36x's reduce and go, or cancel and go away. Then I'm going to distribute the 5 after I've multiplied these two differences squares. So it looks like I have a quadratic equation for now. Subtract from both sides, and we get, at this point I can divide by -5, and I get -9 equals x squared. I actually made a mistake. This should be a negative on the left side, so I end up with a +9. Negative divided by negative is a +9. Now I get a quadratic, so I'm going to set it to 0. Set it to 0, I'm going to factor it, and I get x equals -3 and x equals 3. This gives me a negative speed, so I toss that out, and I only keep 3. 3 miles per hour is the speed of the current we were looking for. So basically, going up, 15 minus 3 was really only 12 miles per hour. Coming down was 15 plus 3, which was really faster at 18 miles per hour. But they only asked me for the speed of the current. They didn't say find the speed of going up and going down. And that I have found right here. The speed is 3 miles per hour.